Good morning, everyone. Today we are exploring heat exchangers, essential devices that transfer heat between two or more fluids to manage thermal energy in countless applications. From power plants to refrigeration systems, heat exchangers are critical for efficiency and performance. In this lecture, we will cover their working principle, types like shell and tube or plate heat exchangers, and flow arrangement such as parallel and counterflow. We will also discuss their application in industries and factors affecting performance, like flow rates and fouling. By the end, you will understand how heat exchangers are designed and applied to optimize energy use in systems like car radiators or chemical reactors. These devices are vital for reducing energy waste and enhancing sustainability in engineering. So let's see into the world of heat exchangers and see how they facilitate efficient heat transfer across diverse industries. Let's start with the basics of heat exchangers. A heat exchanger is a device which is designed to transfer heat between two or more fluids, which may be liquids, gases, or a combination at different temperatures. The fluids are typically separated by a solid wall to prevent mixing, though some designs allow direct contact. This process is crucial in industries like power plants, where steam is condensed, or in refrigeration, where heat is removed from a coolant. Heat exchangers are also used in chemical processing, HVAC systems, and food productions to control temperature efficiently. By enabling heat transfer without direct mixing, they optimize energy use and maintain system performance. For example, in a car radiator, hot coolant transfers heat to air, cooling the engine. Understanding heat exchangers is key to designing systems that balance thermal efficiency, cost, and reliability. So let's explore the working principle to see how heat transfer occurs in these devices. The working principle of heat exchangers involves transferring heat from a hot fluid to a colder one through conduction, convection, and sometimes radiation. Conduction occurs through the solid walls separating the fluids, while the convection drives heat transfer within each fluid. The two primary flow arrangements are used. One is the parallel flow, where both fluids move in the same direction, and the counterflow, where fluids move in opposite direction. Counterflow is generally more efficient because it maintains a larger temperature difference across the exchanger, enhancing the heat transfer. For example, in a counterflow heat exchanger, a hot fluid exceeds temperature can approach the cold fluid's inlet temperatures and maximizing its efficiency. These principles are applied in systems like industrial boilers or air conditioners. Understanding flow arrangements and heat transfer model helps engineer to select the right design for a specific application, ensuring optimal performance. Let's move on to the classification of heat exchangers based on constructions and flow. Heat exchangers are classified based on construction and flow arrangement. By construction, common types include shell and tube, plate heat exchangers, and fin tube exchangers. Shell and tube designs features tubes inside a large shell, ideal for high pressure applications. Plate heat exchangers are stacked plates for compact, efficient transfer, while fin tube exchangers enhance heat transfer with extended surfaces. By flow arrangement, heat exchangers are categorized as parallel flow, counter flow, or cross flow. Parallel flow has fluids moving in same directions. Counter flow has opposite directions for high efficiency, and cross flow has fluid moving perpendicularly, common in the radiators. Each type suit specific needs. Shell and tube for oil refineries, plate heat exchangers for food processing, and cross flow for air conditioning. Understanding this classification helps engineers to choose the right heat exchanger for performance, space, and cost requirements. So let's see into the shell and tube heat exchangers, a widely used design. Shell and tube heat exchangers are the common types in industrial applications due to their versatility and robustness. They consist of a large cylindrical shell containing a bundle of tubes. One fluid flows inside the tubes while the other flows around them in the shell, facilitating heat transfer through the tube walls. This design handles high pressures and temperatures, making it ideal for power plants, oil refineries, and chemical processes. For example, in a power plant, hot steam flows through the tubes, transferring heat to cooling water in the shell to condense the steam. The design can be customized with multiple tube passes or baffles to enhance turbulence and heat transfer. Shell and tube heat exchangers are durable and can handle fouling, though they are bulkier than other types. Understanding their operation is crucial for optimizing industrial process where large-scale heat transfer is needed. Next, we will explore plate heat exchanger known for their compactness and efficiency. Plate heat exchangers are compact, efficient alternatives to shell and tube designs. They consist of a thin, corrugated metal plates stacked together with fluids flowing in alternating channels between the plates. They create a large surface area for heat transfer in a compact footprint, making them highly efficient. The plate's corrugated design induces turbulence, enhancing convective heat transfer. Plate heat exchangers are widely used in HVAC systems, food processing, and pharmaceuticals, where space, hygiene, and efficiency are the priorities. For example, in milk pasteurizations, hot water transfers heat to the milk through plates, rapidly heating it without mixing. They are easier to clean and maintain than shell and tube heat exchangers, but are less suited for high pressure applications. Their compact design and high efficiency make ideal for modern space constrained systems. Understanding plate heat exchangers helps engineers to select cost-effective solutions for specific thermal needs. So let's look at the cross-flow heat exchangers in the next slide. Cross-flow heat exchanger features fluid moving perpendicular to each other, offering a balance between efficiency and design simplicity. In this arrangement, one fluid, often air, flows across the tubes or plates carrying the other fluid, typically a liquid like water or coolant. This setup is common in air conditioning units and automotive radiators, where air is forced over tubes to cool a circulating fluid. Cross-flow provides a higher heat transfer efficiency than parallel flow due to better mixing, but is less efficient than counterflow. For example, in a car radiator, the hot coolant flows through the tubes while air passes perpendicularly, absorbing heat to cool the engine. The design is compact and effective for application where one fluid is a gas, making it ideal for HVAC and automotive systems. Understanding cross-flow exchangers helps engineers to optimize the cooling systems where space and airflow are critical. Next, we will explore the wide-ranging applications of the heat exchangers. Heat exchangers are vital across numerous industries. In power plants, steam condensers use shell and tube heat exchangers to condense steam into water, recovering heat for efficiency. Refrigeration and air conditioning systems rely on heat exchangers like evaporators and condensers to transfer heat, enabling the cooling cycles. In chemical and food industries, heat exchanger control process temperatures such as pasteurizing milk or coolant reactors, often using the plate exchangers for hygiene and efficiency. Waste heat recovery systems capture excess heat from the industrial process or the exhaust gases, reusing it to improve energy efficiency and reduce cost. Heat exchangers also play a role in building heating and coolings like HVAC systems that regulate indoor climates. These applications highlight their versatility in managing thermal energy, enhancing sustainability, and reducing the operational cost. By enabling efficient heat transfer, heat exchangers are key to modern engineering solutions. So let's examine the factors which affects their performance in the next slides. Several factors influence heat exchanger performance. The temperature difference between the fluid drives heat transfer, with larger differences increasing the rate as per Newton's law of cooling. Flow rate affects performance. Higher rate enhances convective heat transfer, but may require more energy for pumping. Flow arrangement impacts efficiency, with counterflow being the most effective due to sustained temperature gradients. The type of heat exchanger matters, such as the plate exchangers offers the maximum efficiency but are less durable under high pressures than shell and tube designs. Material selection is crucial as thermal conductivity and corrosion resistance affects performance on longevity. Fouling, the accumulation of deposits on the heat transfer surfaces increases the thermal resistance and reduces its efficiency. For example, in a shell and tube heat exchanger, fouling from scale or particles requires a regular cleaning. Understanding these factors helps the engineer to design and maintain heat exchangers for optimal performance, balancing efficiency, durability, and cost. So let's conclude with a summary of a heat exchanger. To summarize, heat exchangers are essential devices for transferring heat between the fluids, playing a critical role in thermal systems across industries. They operate via conduction, convection, and sometimes radiation, with flow arrangements like parallel, counterflow, and crossflow affecting efficiency. Types such as shell and tube, plate, and fin tube exchangers suit diverse applications, from power plants to food processing. Their applications include steam condensations, refrigeration, chemical processing, and waste heat recovery, enhancing the energy efficiency and sustainability. Performance depends on the factors like temperature difference, flow rate, exchanger type, materials, and fouling resistance. Proper design ensures efficiency, cost effectiveness, and reliability in the systems like radiators or industrial boilers. Heat exchangers are vital for modern engineering, driving innovations in energy management. I hope these lectures has deepened your understanding of heat exchangers and their impact. For the next time, consider how a heat exchanger functions in a systems you encounter, like an air conditioner or car radiator. Thank you, and let's keep exploring the heat transfer.